Welcome to a short series of videos on building a fairly straightforward profit model. It'll be a weekly profit model, a dashboard, cost and demand components, as well as a maximizing profit price decision determined within the context of this otherwise simple looking model. It follows an approach that is common to software development, a process which includes modularization of each of the tasks that are involved in building such a model. On the screen, you will see the very first page, tab, worksheet. I'll typically use worksheet to describe this. And it's a dashboard. It's called Make a Pie Company. There's an accompanying video and description of this model, and again, in the context of spreadsheet engineering. There are slides over here that we'll discuss in a separate video, which allow us, when we move them, if they will move, there we go, we can see things changing a tad. And what is happening is that can change the size of fixed cost, and in this case, the unit cost. You can see the grid that's defined for the price. Even though the price doesn't change, you can see it's trying to update itself, perhaps a little here. There we go. And what's happening here is that the break-evens, which is where this blue curve, profit curve, crosses the price axis. We're making pies in this one. This might change. Okay. And we'll play with that and see how that works. There are several questions in this tab, which you can see it's a work in progress. Questions come from a client who has very specific ideas and is attempting to understand the interaction of demand and cost structures on profit and ultimately in a decision. Here's some of the filling costs for the pie, $3.48 a pie. We will want to sensitize ourselves to that somehow. Sprouted flour dough, maybe sensitize ourselves to that, as well as overhead expenses. What happens if they double, for example? Is that catastrophic? Will the price have to change remarkably? We'll see how that operates. A fourth question here will not be in this analysis, will be in a future analysis about a projection of profit over time. And we'll introduce another profitability metric for that. All starts with an influence diagram. Total profit means calculating revenue and cost. Revenue means calculating the demand for and the price of the product, and those will interact. Total profit is our metric. It will be colored in blue. Pie price is our decision. That will be colored in yellow. Everything else ends up being some kind of a constraint. The fruit filling cost, the unit dough cost, which, along with how much is being demanded and thus produced, creates a total material cost. Unit processing cost and demand will produce a total processing cost. And three costs, the fixed costs, the total material, and the total processing, those will all contribute to total cost. So it is this flow of information. These arrows all move up and over to total profit eventually. Is what is called an influence diagram, which is generalization of decision trees, and is an example of what is known as a directed, that's the arrows, a cyclic, it allows for cycles or not, graph. And all graphs have nodes. Here's a node, and edges. Here's the edge. The arrow is called an edge. A vertex and an edge is the other classification of it. But here's our map. This is the map of this whole project. It's basically saying we need a profit module, we need cost modules, maybe one cost module, and we need a demand module. There is some data given in this problem, and it ends up being processing cost data. You see, it's just raw data, just numbers. A cost model is developed from this, in which, as you can see, these come or should come directly from the data. And this way, there is one source of the truth, just one source. Let me fix this up a tad. Get this out of the way for the moment. So this is not going to be wrapped text here. There we go. A little bit easier to see again. And this will be wrapped. Okay, good. Number of pi's times 1,000. And that dimension needs a little bit of care when we go ahead and do this. And we'll just move this over. And now we're making this table look at the data table. And that's a fundamental principle. That gives us referential integrity. It gives us data integrity as all of this analysis moves through these tables that we're creating. Here's a number of pi's times 1,000. This will be the number of pi's, and I'm going to use that label and a concatenate ampersand. The shift 7 is that. And pop in a caret and a 2, which raises it to the power. And I put all these strings in double quotes. And now other human beings will understand what's going on here. Here's the actual cost. And now we make a new thing called predicted cost in this table. This is all derived. The number of pi's squared is derived, but the original data is preserved here. So I need to also put in this data directly from this table. And now I'm preserving the integrity. If that other table, the data table, were to change, so would this analysis. I just did a Control C and now a Shift down arrow, then a Control V, and that's done. And here I'm using something called the sum product of two columns. One column, and what I'm trying to do here is take the sum product of these two numbers times these two numbers over here. Where did I get these? One of the first things that we might do with this data is make a graph. And there's a reference problem here because I probably changed something. Number of pi's. And it's probably actual cost. If I do this, make this actual cost. There we go. And what I just did on that plot is made a dynamic axis title. Let's look at this just for a moment. Notice a new ribbon appears. It's called Chart Design. And I select this. I'm going to select this. I'm going to remove it and replace it. Say OK. Now we have a blank canvas. So let's select some data. And notice it's asking for a series name. I usually do put a series name in it, making our life a little bit easier sometimes more complicated. Now just use the title of this whole cost analysis worksheet. The X values conveniently are called X over here. And we simply select using the shift down arrow. The Y values are the so-called actual processing costs per 1,000. And we say OK. And I think that will do it. I never put anything up here in the chart data range. It does have a role, but not for most of the applications that I do. Let's go over here and look. There we go. And you can see that it's automatically bringing in the name of the X and the name of the Y again. And it's almost a straight line. If we experiment with it by right-clicking this, one of those blue scatter dots, and this is a scatter plot, and we say add a trend line, it automatically tries to put in a linear trend line, which looks pretty good, by the way. And with that linear trend line, we can also, if we move down here in the dialog box, we can display the equation and display something called R squared, which tells us the percent of deviation. How well does this line depict, and the line is completely described by intercept and slope. How well does this line depict this literally rise over run? Now, the other thing we typically do is we say, oh, okay, fine, we have that. That's wonderful. And we have the equation up there. We could also do a second order polynomial, and I'm craning my head over to be able to read it. It does say a 2. Okay, and automatically it changes this to be a, you can see this, changes it to be a quadratic relationship. It added an X term to it automatically. Now, I'm going to set the intercept to 0 just to simplify it. And actually, I get an improvement in R squared, which will be my hacked together metric for saying what's the best curve. It's a model selection problem. It's not always that. It sometimes is that. So we'll look at that. And notice over here in M and N, the coefficient on X is 0.9331. Yeah, there we go. And the coefficient on x squared is 0.0712. Okay, close enough. Averaging it here, or rounding it here, fine. And you can see that whatever's happening with over here has happened over here. So I just want to go into that just for a brief moment here and talk about, here's the equation that's being estimated, y, which is actual cost per thousand, depends upon how many pi's and how many pi's squared, plus an error term, yes. And these are all normally distributed, by the way. These error terms are in ordinary least squares regression theory, are all that. Now, there's a way to get these parameters directly without invoking anything else. It's native to Excel. And this is the problem of extracting the statistics of this ordinary least squares regression. You can see what's appearing here as I put my cursor into I4, line est, and it takes as its arguments the y first, and then the x's. It's taking two x's, column B and column C. It's taking both the 8 through 24 and the 84 through 576. It's then saying false to something. Well, the false is the constant is 0. It's set aside. And it's saying true to something else. True to something else is show all of the regression statistics that are available. Of course, you have to know what those are. And you can go here to Barker's formulas at MIT and look at how to specify Linus. It's extremely helpful. But now you also see these curly brackets around this. You can't type those in. That's something supplied by Excel. So the formula is technically located here at I4, but it spreads. Now watch, I'm using Shift, and I have to go over all the way, including the constant, which is 0, and all those NAs occur because it's not really enacted, but it is present in the output as 0. And again, using Shift down arrow, cover this area and just this area. And if you don't, you're going to get value errors, you're going to get weird results. Okay, so we have to pay attention to that, to two things. One, that there are two regressors, predictors, drivers. It's actually one driver and a derived driver from it. X is the only real driver here. And by the way, by itself, it works just fine too. I mean, we could have done that, but I wanted to illustrate how you can put in a little more curvature to make it a little bit more precise, and a constant. All of these things have to be in there. And then this row is the coefficient you can see of x squared, coefficient of x, and of course 0 is a constant. The standard error of the coefficients is also here. And if you remember anything about this, the ratio of these are distributed as T, student T statistics. They're following that distribution. And the ratio is definitely going to show us that these are so-called, in the Ronald Fisher theory of the world, significant. Now, what I do, okay, I put my cursor here, right arrow all the way across 3, 4, 1, 2, 3, 4, all the way down, and then holding, I have my left pinky on it actually, holding the shift down, and I'm using my thumb here, holding control down. I then press enter. And what happens is you couldn't see it. It happened instantaneously again. It calculated all of these numbers. Okay. When it does that, in fact, just let me take it all out, equals line est y first, okay, comma, usually put a space in between, and then both x and x squared, comma, set aside the constant, comma, but report all the statistics as true. And then I shift control enter. And there it did it. Okay, good. So I know that works. And I think you may have seen the curly brackets occur. So this is the cost analysis. That's all it is at the moment. But what we're going to use are the x and x squared. It's annoying. That's the word all of us have used over the years, that this Linus puts the coefficients in reverse order to how it's normally written mathematically and would be written in any other model. So in order to get that back, we use something called index match. Now you could say, I could have just referred this variable here, instead of that great big long thing, to this j, and the next one n, to this I, probably a reverse function somewheres. I don't know all the functions in Excel. I have understood that I won't. And here's the index match. Go look this up in your rendering of Winston. I think it's chapters 3 and 4. And it's applied twice. I'll leave you with that. And once again, thank you for your kind attention.